Now that we have completed exam one, we can move on to finding derivatives in a much faster way. So again, as I explained in class many times, learning the limit definition of a derivative is imperative to understanding what exactly are we finding. You have to keep in mind that when we calculate a derivative, we are calculating the formula to find the slope of any tangent line on any curve, on the specific curve. And that slope represents instantaneous velocity. So keeping that in your mind, you have to keep reminding yourself, because as we learn these shortcut formulas, the meaning behind the slope kind of dissipates. The meaning behind the derivative dissipates, and we forget that it represents the slope of the tangent line. We forget that the slope of the tangent line is telling us about the instantaneous velocity at a very specific point in time. And then once we lose that meaning behind the calculation, it makes our application so much harder to understand what to do. So please don't forget everything we learned so far, but now let's take a look at how we would calculate derivatives without using that long formula. So if we take a look at a constant function where y equals 5, for example, the slope of the line is 0, and therefore the derivative at any point in a constant function will always be 0. So a formal proof would be doing the limit definition. So if you're asked to do a proof of any specific derivative theorem, then you are doing the limit definition. And we see that if any constant minus any constant, because that would be the function here, it gives us a limit of 0. And therefore, the derivative is always 0. So taking the derivative of 5, 0. Taking the derivative of 284,000, 0. Power functions. Power functions are going to be calculated by what I call a counterclockwise circle. So we are going to adjust the exponent and then adjust the coefficient. If we take a look at a line, for example, the slope of this line is constant. It doesn't change. There is no change in slope, and therefore, no surprise, the derivative of every linear line is a constant because the slope doesn't change, so it makes sense that the derivative would be constant as well. So taking the derivative of any linear function will always equate to a constant. In the case of taking the derivative of just plain old x, the derivative is 1. Now that you understand, or hopefully understand, the explanation of why the derivative of a line is always a constant number, then the easy way to take the derivative of anything to the first power is to look at the coefficient. So the coefficient of any first power x is going to be the derivative of that term. So for example, examples 2 and 3 here are a little different. We have to use the power rule. But if we were to find the derivative of 2x, it would be 2, the coefficient, because it's linear. If we were trying to find the derivative of 284 times x, it would be 284. And we know this by thinking back in algebra days. Y equals mx plus b. This is mx if we were looking at this as the function and not the derivative. And we know that the coefficient of x in the mx plus b formula is the slope, which, no surprise, makes sense to be the derivative. Now, if we were trying to take the derivative of x to the 4th power, and as of right now, we've learned how to do it with this very tedious formula, and we would get 4x cubed at the end. So let me show you how we can get the same answer, but very quickly by using the shortcut. Head over to my writing tools. So when we are looking at f of x is equal to x to the 4th power, this counterclockwise circle I was talking about is the first thing that you want to do is take this exponent and bring it down in front of the x. And then you're going to come back up and subtract 1 on the exponent, giving us the derivative of this function, x f prime of x to be 4x cubed, which is exactly what you would find if you did the limit definition out. So this counterclockwise circle is how I like to visualize the derivative. You bring the exponent down and multiply it in front. If there is other numbers in front already, you just multiply. Come back up and subtract 1 on the exponent. And we have quite a few more examples to do with that, so no worries. Okay, so this is how the definition is written out. You take n, which is the exponent, bring it down in front, come back up and subtract 1. And this is our power rule. So for these examples, let's do these out. So for this first one, we are going to take this 6 and bring it down in front, come back up and subtract 1. So the derivative of this first function is 6x to the 5th power. For this second one, same thing. We're going to bring the 1,000 and bring it down in front. Realize it wasn't an f function, it's a y function, y prime. And we multiply it by what's already there. So what's already there is a negative sign. So when we take this 1,000 and bring it down in front, we need to make sure to multiply it by the -1 before we come back up and subtract 1. So we get negative 1,000x to the 999th power would be the derivative of that term. Similarly, we take this 4, we bring it down in front. We are going to have to multiply it by this 3 before we come back up and subtract 1. So y prime is equal to 4 times 3x squared, which gives us 12x squared as our derivative. The next rule tells us that the derivative of a sum of functions is the sum of the derivatives. This also holds for the difference of derivatives. So what they're saying is that separate terms in a function can be taken separately. We can take the derivatives of the terms separately and then just add them all together. Same is true about the subtraction or the difference rule. So for example, if we were taking a look at the function f of x is equal to 2x squared plus 3x minus 9, then we can say that the derivative of this function is we look at the first term, bring down the 2 and multiply it in front. So we get 2 times 2, come back up, subtract 1. 2 minus 1. You know what? Let me write this all out. So 2 minus 1 plus 3x. So again, the exponent here is a 1. So if we do 1 times 3x to the 1 minus 1. And then if we take this last term, which technically, since the x isn't there, it's like x to the 0 power, because recall, anything raised to the 0 power is 1. So if we follow the same rules, we would do 0 times 9 times x to the 0 minus 1. And putting this all together, the derivative comes out to be 4x to the first power plus 3x to the 0 power, which is just the number 1. So we don't need to write the x. And 0 times anything is 0, giving us the derivative 4x plus 3. Let's talk about exponential functions. Now, the exponential function is going to be your favorite because it's the easiest to take the derivative of. The derivative of the exponential is the exponential. So e to the x is e to the x. A little harder is the one where we have a constant a, which stands for any real number, raised to the x power. The derivative would be ln of that number times the original function. So there is a little extra when we are doing the exponential function, a constant raised to x, but e to the x is just itself. And the reason why e to the x is just itself is not because it has a different rule than this one. It's just because ln of e is 1. So we could write ln of e to the x, but they're kind of trivial because ln of e is just the number 1. So if we are taking the derivative with combining some of the rules that we've learned, for this first one, e to the x is e to the x for the derivative, and these are separated by subtraction, so I can take their derivative separately. So e to the x derivative is e to the x, and the derivative of a negative 1x, remember, is just the coefficient, so -1. This next one, we see that it's 3 raised to the x power, so the derivative of this will be ln of 3 times 3 to the x power. And that's just following those formulas. Now, I'm not a huge fan of memorization, which is why learning the limit definition is so important, because if at any time you forget the formula, you now have a backup plan. You can apply the limit definition of the derivative at any point in time that you don't remember a derivative rule, and you can derive these derivatives from scratch and not have to memorize any of these. So keep that in mind when you're doing an exam. If you forget the rule, I mean, online it's a little different because you can always check your notes when you're doing an online exam. But if you were doing this in an on-campus course in the future, you can always resort to that limit definition.